Now we're going to take a look at the general second order differential equation or second order system response when we have an underdamped system. So we have our two forms of our standard second order model with our initial condition and our derivative initial condition right here. And we have stated that if our damping ratio is determined to be less than 1, we know that we have an underdamped system, and the roots of the characteristic equation are complex conjugate roots. That's because what's under the radical term in our solution for our eigenvalues or for our characteristic roots is going to be negative. So in this case, if our damping ratio is less than 1, we're going to rewrite our eigenvalues as being squiggle omega n plus or minus omega n times, now what I'm going to do is I'm going to multiply by the square root of negative 1 and then also multiply this, because I'm pulling the negative 1 out of this term right here. It will be 1 minus squiggle squared. Now I'm going to define a new variable called the damped natural frequency, omega sub d, which we call the damped natural frequency. Alright, and it's being defined as being the square root, it's going to be defined as the natural frequency, the undamped natural frequency, omega sub n times the square root of 1 minus squiggle squared. Okay. The other thing that we're going to have to define here is the fact that the square root of negative 1 is the imaginary number. And for electronics, since we already reserve I for the for current most of the time, we're going to define and represent the imaginary number with the letter J. Okay, so doing that, I find now that my eigenvalues are negative squiggle omega n plus or minus the imaginary number times omega d. Okay, so this term right here, omega n times 1 minus squiggle squared, or the damping ratio squared, becomes my becomes omega d, the damped natural frequency, and the square root of negative 1 is the imaginary number. Okay, so we have two different roots. They're distinct, but they're complex conjugate roots. But these solutions are going to be linearly independent, and we know that from solving our second order equation and our characteristic equation, we're going to expect that the solution for x for this differential equation is going to take the form of some unknown constant times e to the lambda 1 times time plus some other unknown constant b times e to the second eigenvalue or characteristic root times time. Okay, so that's our general homogeneous solution, but we want to deal with that a little bit more now that we have complex numbers. So again, I'm going to take that solution and I'm going to go ahead and plug in my eigenvalues. So my homogeneous solution is going to be some unknown constant, a, times e raised to the first eigenvalue, which will be negative squiggle omega n, plus the imaginary number times the damped natural frequency, all of that is times time, plus some different unknown constant times e to the second eigenvalue, which is negative squiggle omega n, minus the imaginary number times the damped natural frequency times time. Okay, but we see that in this solution, e raised to the negative squiggle omega n, or the negative damping ratio times the natural frequency, all of that is in common between the two terms. So I'm going to go ahead and pull that term out and rewrite this as the homogeneous solution being equal to e to the negative squiggle omega n times time, because we're going to have to distribute that, multiplied by the quantity of a, this unknown constant, times e to the j omega dt, plus b e to the negative j omega dt. Okay? Now we have to revisit some of our mathematics to figure out how to handle this. how to handle an exponential function that's raised to an imaginary number. And we can thank Euler for this. We're going to have to use Euler's identity, which tells us that, if we look in our note pack here, Euler's identities tell us that exponential functions to an imaginary number can be related to sine and cosine terms. Okay, so we're going to take that information and we're going to reevaluate this solution. Okay, so I'm going to plug those Euler's identities into this and expand this a bit more. So my homogeneous solution is now going to be e to the negative squiggle omega n t times the quantity of a. Alright, and let's look at the first Euler identity, which tells us that e raised to the positive imaginary number times something is going to be a cosine plus the imaginary number times a sine term. Right, so that's going to be a times the quantity of cosine omega dt plus the imaginary number times the sine of omega d times time. And we're going to expand b using the second Euler identity, this b term right here. It's going to be b multiplied by the cosine of omega dt minus the imaginary number times the sine of omega dt. Okay? Now what I'm going to do is I'm going to combine like terms. I see that I have a cosine term, and the cosine, if I distribute this, will be a cosine and b cosine times omega d, b times the cosine of omega dt. So rewriting this gives me e to the squiggle omega n times time multiplied by the quantity of a plus b times the cosine of omega d times time. And then if I look at my sine terms and combine them, it's going to be a times the imaginary number times the sine of omega dt plus b times the negative imaginary number times the sine of omega dt. And I can combine those two into something that looks like this. A minus b times the imaginary number times the sine of omega dt. Okay, so we see that from the solution so far we're getting sines and cosines out, which tell us that the system is going to oscillate, just as we said it would, just as we expected it would. Okay, so the next thing that we're going to do is we are going to take a look at these terms right here. Remember that a and b are unknown constants. So what I'm going to do is if I add two unknown constants together, I'm going to come up with yet another unknown constant. So I'm going to define a plus b as being a different unknown constant. And I'm going to call that d just so we avoid collisions with C being used for capacitors, or the damping ratio, or excuse me, the damping coefficient. All right, so d times the cosine of omega dt plus, all right, a minus b. A is a constant, b is a constant, so when we take the difference of them, there's going to be another constant, and that's multiplied by the imaginary number. But remember that the imaginary number is just a number. It's just the square root of -1, so it itself is also a constant. So I'm going to take all of this and call this another unknown constant, e. All right? And that's going to be e times the sine of omega dt. Okay, so what that does is that gives us our general solution, the form of the general solution for the homogeneous second-order underdamped system. D and E are unknown constants that can be determined by applying our initial conditions. And what we can do is we can apply our initial conditions to find that if we know what our initial condition values are, if we substitute those in and apply the initial conditions, we find that the values of D and E are going to be given by these values right here that are included in your note pack. Okay, so there's one other thing that we want to discuss with second-order systems, with the second-order underdamped systems, and that is an alternative representation. you may recall from your trigonometry that we can combine sines and cosine functions together into a single function that's either a sine or a cosine, where there's going to be a different amplitude and a single trigonometric function with a different phase shift. Okay, so the linear combination of sines and cosine functions are given by this relationship right here. And by applying that relationship, I can represent this system, or represent the solution, in a different way. So the alternative representation is to apply this relationship right here, and represent my represent d cosine omega dt plus e sine omega dt in a different way. And when I do that, the alternative representation is I'm going to get a different amplitude, f times e to the negative squiggle omega n times time, plus the sine function of omega d times time plus some phase shift. All right, where f is some unknown constant and the phase shift is some unknown constant. And again, by applying initial conditions, we can represent the solution. We can determine the value of f and the phase shift in this form. So these are just two alternative forms for representing the mathematical solution to the second order differential equation and to the second order system.